Welcome to this complete Docker crash course from HackSprint. In this course, you will learn Docker from an absolute beginner level to practical real-world usage. The course explains what Docker is, why companies use it, how containers work, and how Docker simplifies development and deployment workflows. By the end of the course, you will know how to create containers, manage images, work with registries, write Docker files, and run applications inside Docker environments. The course is designed for developers, DevOps learners, cloud engineers, and anyone interested in modern software deployment. It also introduces core Docker concepts such as containers for running isolated applications, images for building and versioning software, registries for storing and sharing container images, and Dockerfiles for automating image creation. Before learning Docker, we first need to understand containers. A container is an isolated, lightweight environment that contains everything required to run an application. That includes application code, runtime, libraries, dependencies, and configuration files. Containers make applications portable. This means an application behaves exactly the same way everywhere. Whether it runs on your laptop, testing server, staging environment, or production infrastructure, the behavior remains consistent. Containers are lightweight because they share the host operating system kernel instead of running a complete operating system. That's what makes containers fast and efficient. What problems Docker solves? Before Docker, developers often face the classic issue: it works on my machine but not on production. Different operating systems, library versions, and dependencies caused applications to fail after deployment. On one machine, an application might work perfectly using Linux, Python 3.10, and a specific set of libraries and dependencies. However, when deployed to production on another system such as Windows with Python 3.8 and different dependencies, the application could fail due to environment differences. Docker solves these problems by creating isolated environments called containers. Each container includes its own dependencies, libraries, and runtime configuration, ensuring consistency across development and production environments. Docker provides several major benefits. It improves scalability by making it easy to scale applications up or down. It increases deployment speed by allowing applications to be deployed faster with reduced downtime. It improves resource efficiency because containers share the host operating system kernel while using fewer system resources. Docker also improves team collaboration by standardizing environments across teams and machines. The typical Docker workflow starts with a developer creating a container that includes everything the application needs to run. The container can then be shared through a registry so anyone can access and run it. Once built, the same container can run consistently across any environment without modification. Instead of manually configuring environments on every machine, developers can instantly run pre-configured containers. This makes software delivery faster, more reliable, and easier to maintain. When we run applications directly on our local machine, one of the biggest problems developers face is dependency issues. And this image demonstrates that problem perfectly. On the left side, we can see the application running locally. The code is a simple Node.js application that requires the Express package. But when the developer tries to execute the app using nodeapp.js, the system throws an error saying, "Cannot find module Express." Why does this happen? Because the local environment does not contain all the required dependencies. Maybe Express was never installed. Maybe a different Node.js version is being used, or maybe another developer's machine is configured differently. This is the classic "it works on my machine" problem that teams constantly face in software development. Now look at the right side of the image. Here, the exact same application is running successfully inside Docker. Instead of depending on the local machine configuration, Docker packages everything the application needs into a container. That includes the application code, Node.js runtime, libraries, dependencies, and configurations. Inside the Docker file, we can see commands like selecting a Node.js base image, copying project files, installing dependencies using npm install, and finally running the application. Once the Docker image is built, the container runs exactly the same way on every machine. And this is why the terminal on the right shows the server running successfully on port 3000. No missing dependencies, no environment mismatch, no manual setup issues. Docker creates a consistent environment everywhere, whether the app runs on a developer laptop, a testing server, a staging environment, or production. The behavior remains exactly the same. And that consistency is one of the biggest reasons why Docker became such an important tool in modern DevOps and cloud-native development. So the key takeaway from this image is simple. Docker solves dependency problems by packaging the application together with everything it needs to run. That means developers spend less time fixing environment issues and more time building actual software. Virtual machines versus containers. To understand Docker better, let's compare containers with virtual machines. A virtual machine includes a complete operating system, virtual hardware, system binaries, and applications. Because of this, virtual machines consume a lot of memory and storage. Containers work differently. Containers share the host operating system kernel while remaining isolated from each other. This makes containers lightweight, fast, scalable, and resource efficient. A virtual machine may take minutes to boot. A Docker container can start in seconds. That's one of the major reasons containers became dominant in cloud-native infrastructure. Now let's understand Docker architecture. Docker has multiple core components. First, Docker Client. This is the command line interface where we run Docker commands. Second, Docker Daemon. The daemon handles building images, running containers, networking, and storage management. Third, Docker Registry. Registries store Docker images. Docker Hub is the default public registry. Fourth, Docker Images. Images are templates used to create containers, and finally, containers themselves. The workflow looks like this. Docker CLI sends commands to Docker Daemon, processes them to images are pulled from registry to containers are created and executed. Install Docker. Now let's install Docker. Visit the official Docker website and download Docker Desktop for your operating system. Docker official website. After installation, open your terminal and run docker-version. Next run docker run hello-world. Docker automatically downloads the image and runs the container. If you see the success message, Docker is working correctly. Images versus containers. Now let's understand images and containers. A Docker image is a blueprint. It contains application code, dependencies, runtime, configurations, and system tools. A container is a running instance of an image. Think of it like this. An image is like a class. A container is like an object created from that class. Multiple containers can be created from the same image. Images are read-only templates. Containers are live executable environments. Some of the most commonly used Docker commands are essential for managing images, containers, networks, and volumes. To check whether Docker is installed correctly, developers use commands like docker-version, Docker version, and Docker info. Images can be downloaded from Docker Hub using commands such as docker pull ubuntu or docker pull nginx, while all downloaded images can be viewed using Docker images. Containers are created and managed using commands like docker run, docker ps, docker stop, docker start, and docker rm. Developers often use docker run-it ubuntu bash to launch an interactive Linux terminal inside a container. To run services in the background, the -d flag is commonly used, such as in docker run-d nginx. Containers can also expose ports to the host system using commands like docker run-p 8080:80 nginx, allowing applications to be accessed through a browser. Docker also provides commands for accessing running containers, monitoring logs, and checking resource usage. For example, docker exec-it container_id bash opens a shell inside a running container, while Docker logs and Docker stats help monitor activity and performance. Docker Compose is another important tool that simplifies multi-container application management through commands like Docker Compose up and Docker Compose down. Developers can build their own custom Docker images using a Dockerfile and the docker build-tmyapp command. Cleanup operations are handled through commands like docker image prune and docker system prune, which help remove unused images, containers, and system resources. Overall, Docker improves deployment speed, scalability, consistency, collaboration, and reliability in modern software development workflows. Applications running inside Docker containers are isolated from the host system by default. To make these applications accessible externally, Docker uses a feature called port binding. Port binding maps a port inside the container to a port on the host machine. For example, the command docker run-p 8080:80 nginx maps port 80 inside the nginx container to port 8080 on the host machine. This allows users to access the application through a browser using localhost 8080 while the application continues running on port 80 inside the container. In the first step, we create a Docker volume named MyData. A volume is a special storage area managed by Docker that exists independently from containers. Next, we start an nginx container and attach the volume using the -v mydata:/app/data option. This maps the Docker volume to the /app/data directory inside the container. After the container starts, we create a file called hello.txt inside that mounted directory. As shown in the terminal output, the file is successfully stored in the volume. Now comes the important part. We completely delete the container using docker rm-fweb. Normally, deleting a container removes all container data, but because the file was stored inside a Docker volume, the data still exists separately from the container. To prove persistence, we launch a brand new container and mount the same volume again. When we check the /app/data directory, the hello.txt file is still there. This demonstrates one of the most important features of Docker volumes, data persistence. Even if containers stop, crash, or get deleted, the data stored in volumes remains safe and reusable across multiple containers. Now let's understand how Docker networking works. In this demonstration, we first create a custom Docker bridge network called MyNetwork. A Docker network allows multiple containers to communicate with each other securely and efficiently. After creating the network, we launch two separate containers named C1 and C2 and connect both containers to the same network. As you can see in the diagram, Docker automatically assigns private IP addresses to each container. Container C1 gets the IP address 172.18.0.2, while container C2 gets 172.18.0.3. Since both containers are connected to the same bridge network, they can directly communicate with each other internally. In the terminal section below, we verify this communication using the ping command. From container C1, we ping container C2 successfully, and similarly from C2 back to C1. The successful packet transfer confirms that both containers are connected and able to communicate over the Docker network. This networking capability is extremely important in real-world applications because services like web servers, databases, APIs, and backend applications often need to communicate with each other inside isolated container environments. Docker networking makes this communication simple, secure, and highly scalable. Docker registries are an essential part of the Docker ecosystem because they provide a centralized place to store, manage, and distribute Docker images. A Docker image contains everything required to run an application, including the code, libraries, dependencies, runtime, and configuration files. Instead of manually setting up environments on different systems, developers can simply pull images from a registry and run them instantly inside containers. The most popular public registry is Docker Hub, where developers can access thousands of official and community-maintained images. Popular images available on Docker Hub include Ubuntu, Node.js, Redis, MySQL, and Nginx. These ready-to-use images help developers save time and accelerate application deployment. The workflow of Docker registries is simple but powerful. Developers create or customize Docker images on their local machines and then push those images to a registry. Once stored in the registry, the same images can be pulled and used by servers, cloud platforms, testing environments, or other developers. This ensures consistency across development, testing, and production environments. Whether the application runs on a laptop, virtual machine, or cloud server, the behavior remains the same because the container includes all necessary dependencies. There are mainly two types of registries: public registries and private registries. Public registries like Docker Hub are accessible to anyone and are commonly used for open-source projects and publicly shared images. On the other hand, private registries are used by organizations to securely store their own custom images. Private registries provide restricted access, improved security, better control, and compliance management for enterprise applications. Large companies often use private registries to manage internal applications and protect sensitive software assets. Overall, Docker registries make it easy to store, share, version, and distribute container images efficiently. They play a major role in modern DevOps and cloud-native workflows by enabling faster deployments, better collaboration among teams, and reliable software delivery across different environments. One common confusion for beginners in Docker is understanding the difference between a registry and a repository. Although the terms sound similar, they represent different concepts in the Docker ecosystem. A registry is the complete image hosting service where Docker images are stored and distributed. You can think of a registry as a large online library that stores thousands of Docker images. The most popular example is Docker Hub, which is the default public registry used by Docker users worldwide. Organizations can also create private registries to securely manage their internal container images. Inside a registry, we have repositories. A repository is a collection of related Docker images grouped under a specific name. For example, inside Docker Hub, repositories like nginx, Node, and Redis contain images related to those technologies. Each repository stores multiple versions of the same image so developers can use the exact version they need for their applications. These versions are identified using tags. Tags help differentiate image versions within a repository. For instance, the nginx repository may contain tags such as latest, 1.25, or Alpine. This allows developers to pull a specific version depending on project requirements. For example, running docker pull nginx:"latest" downloads the latest version of the nginx image, while docker pull nginx:1.25 downloads a particular release version. Tags are extremely important because they help maintain consistency across development, testing, and production environments. In simple terms, the registry is the platform or service that hosts images. Repositories are categorized collections of related images inside that registry, and tags represent different versions of those images. Understanding this hierarchy makes Docker image management much easier and helps developers work more efficiently with containerized applications. Now let's move into one of the most practical and important topics in Docker: Dockerizing a Node.js application using a Dockerfile. A Dockerfile is basically a text file that contains a series of instructions used by Docker to automatically build an image. Instead of manually installing dependencies, configuring environments, and setting up applications every single time, we can define everything once inside a Docker file. Docker then follows these instructions step by step and creates a portable image that can run anywhere. This is one of the biggest reasons why Docker became so popular in modern software development and DevOps. In this example, we are creating a simple Node.js application and then packaging it into a Docker container. On the screen, you can see the structure of the project. Inside the project folder, we have files like app.js, package.json, package-lock.json, and the Docker file itself. Let's understand what each file does. The app.js file contains the actual Node.js application code. In this example, we are using express.js to create a small web server. The application listens on port 3000 and returns a simple message saying, "Hello from Dockerized Node.js app." Next, we have package.json. This file contains metadata about the project along with all the dependencies required for the application. It also defines scripts like npm start. The package-lock.json file stores the exact dependency versions. This ensures consistency across installations so that every environment uses the same package versions. And finally, we have the Dockerfile, which is the most important file for containerization. Now let's break down the Dockerfile instruction by instruction. The first instruction is from node:20-alpine. This tells Docker which base image to use. Here we are using the official node.js image provided on Docker Hub. The version is node.js 20, and it is based on Alpine Linux. Now you may wonder why Alpine is used. Alpine Linux is a very lightweight Linux distribution. It keeps Docker images extremely small, secure, and efficient. Smaller images mean faster downloads, faster deployments, and lower storage usage. This is why Alpine-based images are commonly used in production environments. Next comes workdir/usr/src/app. This instruction sets the working directory inside the container. Think of it like changing directories in a terminal using the cd command. From this point onward, every command will execute inside this folder. If the directory does not already exist, Docker automatically creates it. After that, we use copyPackage_star.json./. This command copies package.json and package-lock.json from the local machine into the container. Now, this step is actually a very important optimization technique. Docker uses a layer-based caching system. Every instruction in a Docker file creates a separate layer. By copying only the package files first and installing dependencies before copying the rest of the application code, Docker can reuse cached dependency layers whenever the dependencies remain unchanged. That means future builds become significantly faster because Docker does not reinstall packages every time. This is considered a best practice when writing Docker files for Node.js applications. Next, we have run npm install. This command installs all the dependencies listed inside package.json. The installation happens inside the container itself, meaning the container gets its own isolated dependency environment. This is one of Docker's biggest strengths. The application no longer depends on software installed on the host machine. Everything required to run the app exists inside the container. That means even if another machine has a completely different operating system or configuration, the container will still work exactly the same way. After dependencies are installed, we use copy ... This copies the remaining application source code into the container. At this stage, the entire Node.js application is now available inside the Docker image. Next comes expose 3000. This instruction documents that the application inside the container listens on port 3000. Now it's important to understand that expose does not actually publish the port outside the container. It simply acts as metadata and helps Docker networking tools understand which ports are being used. The actual port mapping happens later when we run the container. Then we have env port equals 3000. This creates an environment variable inside the container. Environment variables are extremely useful because they allow applications to be configured dynamically without modifying source code. For example, in production environments, applications often use environment variables for database credentials, API keys, configuration values, and runtime settings. In this case, we are simply defining the application port. Finally, we have cmd open bracket. This demo shows the complete lifecycle of running an application using Docker, starting from building the image all the way to opening the application inside a browser. In the first step, we build the Docker image. The command shown here is docker build -t demo-app:\latest. What this command does is package the entire application together with its dependencies, runtime environment, and configuration into a portable Docker image. As we can see in the terminal logs, Docker follows multiple steps defined inside the Docker file. First, it loads the build definition and metadata. Then it pulls the base image, which in this case is a Node.js Alpine image. After that, it creates the working directory, copies the package files, installs dependencies using npm install, copies the application source code, and finally runs the build command. At the end of the process, Docker exports everything into a reusable image named demo-app:/latest. This image now acts like a blueprint for creating containers. The advantage is that this same image can run consistently on any machine without worrying about operating system differences or missing dependencies. In the second step, we run the container using the command docker run -d -p 8080 :8080 name demo-app:/latest. Here, Docker creates a live container from the image we built earlier. The -d flag runs the container in detach mode, meaning it runs in the background. The -p 8080 :8080 option maps the container port to the local machine port, allowing us to access the application from the browser. The --name option gives the container an easy-to-recognize name. Once the command executes successfully, Docker generates a unique container ID. We can also verify that the container is running by using the docker ps command, which displays details such as container ID, image name, status, and exposed ports. The status message confirms that the container is running successfully and the application is now accessible at localhost port 8080. Finally, in the third step, we open the application in the browser. By visiting http://localhost:8080, the deployed application becomes visible just like a normal web application. In this demo, we can see a modern dashboard interface containing analytics cards, sales data, recent orders, navigation menus, and different management sections. This proves that the application is successfully running inside a Docker container while still being fully accessible through the browser. Overall, this workflow demonstrates one of Docker's biggest advantages: portability and consistency. Developers can build the application once, package it into an image, and run it anywhere without changing configurations. This makes deployment faster, simplifies collaboration between teams, and eliminates the common problem of applications behaving differently across environments. So you can also debug your application directly in Docker, and this is actually one of the most useful things when something isn't working as expected. Instead of guessing the problem, Docker gives you tools to inspect what's happening inside the container in real time. First, you can check the logs of a running container using the docker logs command. This helps you see startup messages, errors, warnings, or any requests reaching your application. If your app crashes or refuses to start, logs are usually the first place you should look because they often tell you exactly what went wrong. Next, if logs alone are not enough, you can actually enter the running container using docker exec-it. This opens a shell inside the container, allowing you to inspect the environment directly. From there, you can check files, verify paths, inspect installed packages, or simply confirm whether everything is configured correctly. And finally, you can also inspect files inside the container to make sure your application files are present and properly deployed. For example, if a website isn't loading correctly, you can navigate through directories, check configuration files, and verify whether the expected files actually exist. So overall, Docker not only helps you run applications in isolated environments, but also gives you powerful debugging capabilities. Whether it's checking logs, entering containers, or inspecting files, these small steps can save a lot of time while troubleshooting issues. And that's a wrap on your Docker journey. From understanding containers and images to mastering networking, volumes, Dockerfiles, and deployment basics. You've built a strong foundation in one of the most important technologies powering modern software today, but this is only the beginning. Next up, Docker Compose, Kubernetes, CI/CD pipelines, and cloud platforms like AWS ECS and Google Kubernetes Engine. Keep building, keep experimenting, and keep learning, because the future of software runs on containers. So with this, we wrap things up. See you in our next videos on Docker Compose and Kubernetes. Feel free to check out the description, all the necessary links are there. Also check out our demo courses and upcoming projects from HackSprint. Keep learning, keep building, and most importantly, build anything.